Thank you, Micah, and thanks to everybody for showing up for my talk today. I'm going to be talking about stealth assessment in games to measure and support 21st century competencies, which Micah already mentioned. And along the way, I'll be describing the what, why, and how. So part of the how, part of the why right now is shown here. So if you look at this graph, you can see that there's a big problem here. In the United States, there's a real disproportionate amount of men, white males, that are in science and engineering workforce. This is in the United States, and I'm not sure how it holds up elsewhere, but it's a real disproportionate number of white males. So for a long time, for probably a decade, my goal has been to get more girls and other kinds of underrepresented minorities excited about STEM and deepen their learning in STEM areas. And it turns out that well-designed digital games can do both, and ultimately increase the diversity in the field. So before I start, I'm going to just give a very simple definition of what a game is. So the most succinct definition I think I've heard is by Valerie SHUTE, and he defined a game as unnecessary obstacles that we choose to overcome. And a really good example of this is golf. So the goal in golf is very simple, right? You got to get a ball into a hole. But when you introduce some of the obstacles or challenges, it gets more difficult and all the more compelling. So you've got to hit that ball with a stick that has a club on the end of it, and you've got to slam it from like 30 yards away or 200 yards away from the hole. And so when I'm going to be talking about games, I'm going to be talking, the basic definition applies, but I'm going to be talking about digital games. And these are games that can be played, on gaming consoles, on mobile phones, tablets, computers, and so forth. So why use games as assessment? Micah earlier just introduced one of the reasons is, we're still doing the same kind of testing that we've done for the last 100 years, with regard to multiple choice kinds of testing and so forth. But games are a viable alternative. So good games are very engaging, compared to who likes to take tests. And they actually require a player to apply the knowledge and skills in order to succeed. And games are also ubiquitous. Pretty much all US households have at least one person who plays video games regularly. And I think that probably that statistic holds up all around the globe. So digital games differ along many dimensions, the genre, the platform, the content, but I've contended that good games are a system, and they consist of these 6 elements right here. So the first one is interactive problem solving. So this represents the constant interplay between the player and the game and the player and the game, and it's usually in the context of solving some meaty, interesting kind of problem. Good games offer specific goals and rules, and this allows the player to know what to do, when, and how. They provide adaptive challenges, and this represents the balance between the difficulty level of the current game and the section that they're in and the ability of the players. And good games kind of hover at the outer edges of doability. They offer control to the player of the gameplay and their learning. Good games offer ongoing feedback, and this is, as everybody knows, critically important for learning. And they offer sensory stimuli, which is in the form of graphics or sounds or a narrative. So when all these elements come together, it makes for a very, very engaging kind of experience where players want to play and replay games and solve really hard levels, because reaching goals is such a hugely satisfying experience. So now the question is, this is the hard part of the whole story. how can we measure and enhance learning in games without mucking up the fun factor, without disrupting flow? And that, of course, is the segue into stealth assessment. So I've shown this slide before. This is a simple cycle of what stealth assessment is doing. So a kid or kids are playing a game. They're completely immersed in gameplay, and they're producing a whole bunch of performance data, and those data are captured automatically in a log file. This is with all games. Some log files are better than others. And then those data are automatically scored. They're analyzed and scored with the stealth assessment machinery. And then those scored log file data are updated into the student model at any time and any grain size. And then those current estimates about how well a person is doing are then provide the basis for feedback and other kinds of support back to the player who continues to play the game, produce more data, which gets analyzed and so forth. So round and round the cycle goes. Now, these are some of the features of stealth assessment that I've been arguing for, I guess, for the last 10, 12 years or so. The first is that stealth assessment should be seamless and ubiquitous. And by seamless, I mean that the stealth assessment is buried deep into the code of the game so that it's invisible, and learning and assessment become blurred. Ubiquitous means that it's running at any and all times. The next feature is that it could be used for summative purposes, but my strong preference is that it should be used for formative purposes. So it should serve to support the learner and not, serve as judge and jury and, make evaluations on the basis of, single scores. And finally, it's intended to produce accurate and rich models of the learner, which is made possible because we build the models in stealth assessment using something called evidence-centered design, or ECD. So this is a very simple model of the three main models of evidence-centered design. This was originally formulated by Bob Mislevy, Linda Steinberg, and Russell Almond. And there's two main foci of ECD. It provides a way to reason about assessment design, how to create an excellent assessment, and it provides a way to reason about student performance. So when we go here from left to right, this lets us create really good assessments. And it always starts with the competency model. This is what all do you want to say about the person at the end of the day in regard to their knowledge, their skills, their dispositions, or whatever it is that you're looking at. These are theoretical variables. Okay, so after the competent, and it's usually what we've been doing since the beginning is to do a deep dive into the literature, come up with a literature review, and then a graphical model of the relationship of all the relevant variables, whether it's for physics or creativity, and then send it off to experts in the area who then review the literature as well as the associated model and provide feedback. And then, so it undergoes some validity at the very beginning of the story. So after the competency model is established, then we work on the evidence model. And this involves establishing specific relationships between those theoretical variables and their associated metrics, how you're going to measure them. And finally, after you set up the measurement or the evidence model, there's the task or the action model, which involves defining specific features of tasks that'll let you elicit the evidence that's needed. So now when we reverse the flow, when we go from right to left, it lets us accomplish diagnosis. So say a kid is playing a game, they just solved a level, or they didn't solve it, they quit out of a level. So there's this yellow box right here, if you can see it. This is specific behaviors or indicators that they did in the game that's sent to the evidence model. And the evidence model immediately parses and scores it. Again, this comes directly from the log file. So it's parsed and scored. These are observables, measurable data right here. And then the second part of the evidence model actually takes those observed data and statistically links them back to their relevant competency node or variable. And then those updated nodes here are reinserted back into the competency model. That's evidence accumulation. And so that we know at any time and also at any grain size how well or poorly a kid is doing. Over the past, I guess, 12 years or so, we've tested out stealth assessments to measure a range of different knowledge and skills. And like I said, we always start with a deep dive into the literature to develop the competency model. Some of the ones that we've developed stealth assessments for include physics understanding, problem-solving skills, creativity, collaboration, calculus, persistence, systems thinking, spatial skills, a bunch of them. I have a QR code right here, which will take you right to a link to some relevant papers on some of those different stories. And we've also used different games in which to embed our stealth assessments, some of which we've developed in-house. So we developed Physics Playground and we developed Penguin Go. This is for computational thinking skills. And we've also embedded it, which is a lot harder to do in commercial games because invariably they will not be tracking in their log files the kinds of stuff that we want. So we have to go back and re-engineer or retrofit stuff to be collected in the log files. But Plants vs. Zombies, Portal 2, Minecraft, variant limits, and so forth. So I'm going to now show you how it works in a game called Physics Playground. So you get a sense for, how it actually looks and feels in a particular game. So Physics Playground, it's a computer-based game with 2D physics simulations for things like gravity and mass, potential and kinetic energy, and so forth. And the goal across all the hundreds and hundreds of levels, there's unlimited levels because we also built out a level editor in the game so we could create any kind of levels. And kids can create levels and teachers can create levels. But the goal is always the same: get a green ball over to hit a red balloon. And there's two different types of levels. The original kind, we used a sketching interface. This is like, I was inspired by a game I played about 13 years ago that I loved called Crayon Physics Deluxe. And it had a sketching interface where you draw stuff and it comes to life. The same thing here. The player is using a mouse or a stylus to draw objects directly on the screen using colored markers, and they come to life. They assume physical properties. So they're creating things like pendulums and levers and springboards and so forth. And then more recently, about the last 3 years or so, we developed a series of manipulation level types. And here the player is using a slider and making changes to different physics parameters like the mass of the ball or gravity. You can set gravity to 0, and that's really cool. Air resistance and bounciness of the ball and stuff like that. I guess I also want to say that players, there's not one correct answer that is acceptable because you can solve a lot of these levels many different ways. Some are better and more elegant than others. Before I move on, these are some of the original funding for this was the Gates Foundation. We've got a lot of grants from NSF and IES to support this development. We've done lots of really cool experiments, and we have one big one coming up. I'll tell you about one recent one in a few minutes. But I also want to introduce you to the team. It's not just me. I work with a bunch of really cool and smart people. And here's some of them here. Let's see. So I think I shared my sound. So I'm going to show you what the look and feel of the game looks like right now. Y'all can see. It's going to start with a sketching level. Here, a person is drawing a pendulum to solve it. The arm is the right length and the angle is good. It's got a good mass, and the timing is important here to get the ball right up at the right time. Here, a person's using the dorsal fin as a fulcrum. They're drawing a weight. They're going to pop it over to hit the balloon. And there is, like I said, it's so much fun to create levels and also to play the game as well. Here's an example of a manipulation level right here, where it starts off and it shows what it does in regular world. And then the person here is changing the mass and the air resistance just enough so that the mass tilts it over and it's it. I should have given you kind of a look and feel for the game. So because we needed levels that differed in terms of difficulty to satisfy all the different types of players, we came up with these general difficulty indices that we used. And then we took all the different levels that we had in this study I'm going to be talking about. We had like 150 different levels, and we rated them in terms of these difficulty indices, and then we arrayed them from easiest to hardest in various playgrounds. So some of these difficulty indices are things like the relative location of the ball to the balloon. So if the balloon is below the ball, it makes the problem really simple. You can just draw a ramp and slide the ball on down to get it. But if the balloon is above the ball, it makes it a little harder, and you've got to create some object that can exert some force on the ball to elevate it, to defy gravity. The number of obstacles that are in the problem is a measure of difficulty. You can have no obstacles or a lot of obstacles. The simple machines that I talked about, lever, ramp, pendulum, springboard, in the game we call those agents of force and motion. So if there is more than one agent of force and motion needed to solve the level, it would be harder. And the novelty of the problem was also another indicator of difficulty. And I'll show you two examples. This is a pretty easy springboard problem, and this is a little more difficult one. And you can see how they're played. Now here, the balloon is a little bit above the ball, but there's no obstacles in the way and stuff like that. So it's not that hard. It was classified as fairly easy. So here the person is going to create a springboard, very simple. And then looks like they're going to affix a weight to it, and then it'll drop down, and they release the weight and it pops up and solves it, no problem. Now in this one, the second one, I speeded this up because the person here took about 12-13 minutes to solve it. So I speeded this up. But you can see that there's a lot of obstacles between this ball and where the balloon is sitting over there. So you can see how the obstacles make it so much more difficult. So the first attempt, their mass was too much, so it overshot where it needed to go. So they reduced the mass a little bit, and then they ran into the problem with the hat right above it, which created an obstacle. So they tried another one, and then the mass gets stuck down there. And then they try another solution, but again, the timing becomes important because you have to wait until the ball is at the very end, and they've now learned that. And so I think this is the one that eventually gets it in. So now they're just waiting for the right time, and it goes in. So that's a medium level difficulty. I should have showed you one of the harder ones. Those are kind of sadistic. Okay, so let's start with the competency model underlying physics playground. So overall, for the physics that we're looking at, our main facets are force and motion, linear momentum, energy, and torque. And then these guys are, these guys over here are the 9 primary physics concepts that we want to measure and support in the game. So each one of these has, at least 10, maybe 10, 20, 30 different levels of varying difficulty that are associated with each one of those different primary concepts. So that's the competency model. Now, in terms of the evidence model, remember that I said that, basically we're just pulling out information from the evidence model and we're automatically from the log file and automatically scoring it. I'm going to show you one example of some automated scoring of a really difficult problem that we had. So a lot of stuff in the log file is really easy to score, right? So like if I want to know how long did a person spend on a level, I know what their start time and their end time is. So it's just the difference between those two. And other things too, number of objects drawn is a straight count. But when people are in the sketching levels are drawing objects, how do we know that what, one person is drawing is a pendulum? Because we all draw things differently. So how can the computer actually tell what these different objects are? How can they classify them into the different agents of force and motion or simple machines that we're interested in? So this is an example of a log snapshot from the game, and I don't expect you to see it. So this is a blown up part right here. This is for one level. And so we see this is called the diving board level right here. We see that the person spent 149 seconds on the level, so about a little over 2 minutes to solve this level. They ultimately solved the level. And some other data are present in here too, but look at this that I've highlighted here. So here this is saying at timestamp 61.78, the person created a springboard and then it didn't work. And then at 98.08, they created another springboard. So how in the world does the computer know that what they drew was in fact a springboard? So from the very beginning of this, we've always had at least 2 physicists working on the project with us. That's to keep us honest and knowledgeable. So we had a meeting early on and everybody met together for 2 full days. And for the first day, we all kind of sat around and brainstormed how the computer was going to make this identification, this classification. And we talked about things like computer vision and stuff, and we realized none of us had any expertise in computer vision. But at some point we came up with a very elegant solution to the problem. And I'll show you what I mean here. So basically, each one of these agents has its own set of unique features associated with it. So I'll give you an example with a pendulum. So here, there's 2 different phases. The first phase is the monitor phase, where the computer is saying, I think what the person has drawn is a pendulum. The object has a single pin. It's rotated more than 20 degrees and it has non-zero rotational velocities. So that's the weak hypothesis. And then when the next condition fires, then that says, yes, it is a pendulum. So that's when the ball has moved moderately since the monitor trigger. So with just those simple rules in place, we're able to accomplish more than 98% accuracy between what the computer is classifying as one of these agents and what humans are saying on the screen, which was really, really important and good because we want to be accurate, right? So now in terms of the evidence model, I just mentioned, the evidence identification. That means, so we had to start by saying what the rubrics were, that let us automatically score the raw data that comes from the log files. Again, these are observables and we call them indicators. And some of the ones that we capture and use are things like time to solve, a level, what objects were drawn, sliders, number of restarts. Did they get a gold coin? They could solve a level and get a silver coin just by, working through it. But if they solve it in an elegant solution, they get a gold coin, which was a proxy for mastery. That was basically solving it under par. So that's evidence identification. So we could use those data, and now we've got hundreds, if not thousands of students' data, and we could actually determine cut scores from the frequency distributions of any of the indicators. So for instance, as far as levels solved, we could see that, in a 2-hour period, the majority of people, on average solve, between 30 and 70 levels. So that's kind of medium, and we know what low is and we know what high is. So we establish cut scores, and then we can use that information during our formulation of our Bayes nets. So every level in the game has its own little mini Bayes net associated with it. And I'll show you an example in a second. So during gameplay data for every indicator, so a person is at a level and they do some stuff in that level. This example here has to do with a manipulation level, it looks like. So these are the indicators. Those instantiated score data then are fed back into the little mini Bayes net, and then the mini Bayes net is back into the giant competency model or student model, which then propagates at any time. So what's important to know is that we have one Bayes net for every level. And my colleague Russell Allman has a whole suite of tools. I have the link to that down here that can allow you to generate Bayes nets. Back in the very early days of this project, we were creating Bayes nets by hand, and now we can automatically generate them based on some automated Q matrices, which is beyond the scope of this presentation. But a Q matrix is basically taking all the different levels of the game, assigning which of those 9 targeted physics competencies are relevant to that level, its difficulty level, and so forth. So that's the Q matrix that can then be converted into a Bayes net for that level. So that was a very sweet tool. Here's an example of one level. This is the manipulation level, and its own, little miniature Bayes net that I just showed you. So the question here now becomes, we have a good handle on how to measure competencies, but now the question is, how can we use that information to enhance learning? And so now I would like to segue into the learning supports of the story. So in the last 3 or 4 years, we've been getting support from NSF and IES to develop some, I guess I can call them stealth learning support, because again, what we don't want to do is disrupt gameplay or enjoyment. So we started off, and we've been developing a whole lot of different, we broke them out into cognitive supports and affective supports. So so we've developed a whole lot of these different kinds of supports, and we've tested them out in multiple usability and experimental studies to see which works and which don't, and so forth. So as far as some of the game supports, we have things like worked examples. These are very short video solutions of an expert solving the level. So if somebody gets stuck, you can go see one of these things. And in some of the early studies, we saw that people were abusing those, and they would go and see the worked example and then come back and just copy it. And we thought, well, that's no good. So we then implemented an incentive system into the game, which is now operational and working as intended. So now we charge kids $60 to see a worked example. They make money in other ways by solving levels and seeing some of the physics supports. So we have game support ones. We also have supports specifically related to the physics in the game. So this is more about the game mechanics. This is about the underlying physics. So I may understand how to solve a level with a pendulum to get the ball to hit the balloon, but what are the physics that go into that? That's where our physics videos come into play. These are very short 1-minute videos that for every level, we show what the underlying physics are. And we have a narrator, and we used first principles of instruction by Merrill and First Principles of Multimedia by Rich Mayer to create these. And we also used in the physics videos, I'll show you an example of one in a second. We also used the same narrator for consistency. We also used the same background as the game to give it a, a familiar kind of look and feel. We also had interactive definitions where they could build out definitions of, what is potential energy. We have little mini animations. We had formulas. We had Hewitt videos, which are kind of cartoon versions of some of the different concepts. And we had a glossary of terms. So I'm not going to talk about the affective supports because those would take us too far afield. But the same thing holds, when a person is confused or they're frustrated or they're bored, they're not going to learn. So we've got to turn that train around. And that's where our affective supports come in. In some cases, if they're too frustrated, we want to kind of take them out and let them do something else for a minute to redirect their attention and get them centered again. Again, the trick, like I said, is trying to create different learning supports and insert them in gameplay so they don't disrupt flow. So here's an example of one.
Here you're going to see how to transfer energy to the ball using a lever. Gravitational potential energy, or GPE, is the energy of height. The ball begins with no height, so it has no GPE. The object has lots of height, so it has lots of GPE. Energy can change forms. The object lost GPE as it fell, but it gained kinetic energy as it sped up. Kinetic energy, or KE, is the energy of motion. Energy can transfer from one object to another. The ball gained GPE, it gained height, and it gained KE. It's now moving.
And they can
here you're going
to see those videos, as often as they want to. Okay, so now I'm going to end the story with a research study that we recently conducted. This was done right before COVID hit. We've since done other experiments during COVID that have been fully online, but this was done face-to-face. We had 263 kids. They were 9th to 11th graders. In their science class, we tested across 6 different days, and there was about 4 hours of gameplay altogether. I have a link down here, which is a paper that we wrote and published that tells the big story to all this. I'm going to give you a very abbreviated version. So the kids played both sketching and manipulation levels. There was 91 levels altogether. There was a full set of 8 different, and these were all the cognitive supports that were present. We had a physics pre-test and a physics post-test, and then at the end we gave a game and learning support questionnaire to see how much they enjoyed the game. Maybe the people that got the supports, found them to be tedious and disruptive and hated the game because of it. We'll see what happened. So as far as the research questions, I will tell you about the following. So first research question, and this is always the first one we do in any study, is to determine the psychometric qualities of the stealth assessment measure. So I can say I'm measuring physics or creativity, but am I? So the first thing we do is ask, are the stealth assessment measures reliable? Are they valid? And are they fair? The second question has to do with learning and enjoyment. So do kids overall learn any physics by playing the game? And do they enjoy the game? And the last question has to do with the learning supports. Which one of the learning supports most effectively enhance learning and game performance? Good questions, right? So as far as reliability, first we looked at the reliability. So if our external measures weren't reliable, then we couldn't say anything about our in-game stealth assessment measures. So step 1 is determine the reliability of our external measures. And the reliability is good. Pre-test was 0.77, post-test was 0.82. I'll show you what, so we patterned the post-test after the FCI, the Force Concept Inventory, which is kind of the gold standard for this content that we're targeting. And as you can see, these are, typical multiple choice kinds of questions that kids are familiar with. So you've got, a balance beam right here, a scale, and you've got 2 blocks here and it's balanced. So what's the weight of this block right here? This is 1 kilogram, and 1 kilogram is 20 centimeters. Anybody want to shout out the right answer? This is half the distance from these 2 blocks right here. Come on, somebody knows the answer. Okay, I'm using my 4.
D?
4, yes, D. So our external measure is reliable. And then looking at the reliability of our stealth assessment measures, I actually looked at it from different angles. So first I computed a confirmatory factor analysis, and I looked at the number of gold coins that people got across the different agents. And like I said, that was kind of our proxy for mastering the underlying concepts, ramps relating to Newton's first law and so forth. And the fit was great, and the error was small. And so that was good. I also computed an interclass correlation with those same data and found it to be 0.85. And then at some point I realized I could compute a Cronbach's alpha, the stealth assessment data. So I identified 110 cases where they solved this, because in this version of the game, it was nonlinear, which means that a person can solve any level in any playground that they wanted. So not everybody solved the same levels, but I found 29 levels that everybody solved. Computed a Cronbach's alpha and found it to be 0.87. So at this point, we're comfortable that the stealth assessment measures, are reliable. So in terms of validity, what we did was we looked at the correlation between our in-game estimates and our external measures. So with our external measures, as with our in-game measures, we had an overall score on the pre-test and the post-test. And we also broke it down by facet. And in all cases, we see that the correlations are significant, which was really good, because now we could say, yes, what we're measuring does match with, FCI kind of constructs. Any questions so far? Oh, I guess I'm not sure what time it is, 9:43. I guess I have a couple minutes left. Is that right, Micah?
Yeah.
Okay. So in terms of fairness, that was the last of the kind of psychometric questions. We had about the same number of males and females in our sample, and we had a wide range of ethnicities. And what we found first in looking at learning by gender, boys started out with a higher physics pretest score than the girls did, but we computed an ANCOVA, and the result with our dependent variable being gender, being the post-test score, our independent variable was gender, and we used pretest as the covariate. And what we saw was at the end of the day, there were no significant outcome differences by gender holding pretest constant. So we could actually see the girls improve quite a bit relative to the boys' improvement, which was a really good thing. Remember my initial slide that, the diversity issue in science and engineering is way out of whack. And similarly for ethnicity, we had, of our major ethnic groups, we had whites, Blacks or African Americans, and Hispanic. And whites came in with higher incoming pretest knowledge, no big surprise there. But at the end of the day, the results showed no significant outcome differences by ethnicity when holding pretest constant. And that was really very satisfying as well. Okay, as far as learning and enjoyment, all students scored significantly higher on the post-test than the pretest. And the control group showed no pretest to post-test differences. So there was some learning going on. In terms of enjoyment, we used a scale that had about 5 enjoyment items, and it ranged from 1, I hated it, to 5, I loved it. And overall, kids really enjoyed the game, on average about 4.03 on this 5-point scale. Males and females enjoyed it equally, and that's not always the case with different kinds of games, so that was really good. And by ethnicity, whites, blacks, and Hispanics all equally enjoyed it as well, which was wonderful news. And finally, as far as learning supports, the favorite supports, and these were in terms of frequency of usage. In this experiment, we actually had kids could choose or not. It was under voluntary control, so they could choose to see learning supports if they wanted to. So the favorite supports were hints, physics videos, and worked examples. These are the kind of cheats I told you about. As far as predicting learning, I computed a regression analysis with post-test as the dependent variable and pre-test and all the different eight support frequencies in the equation. And only pre-test and the physics video significantly predicted outcome, which is post-test score. As far as predicting gameplay, the same thing. Those who watch more physics videos also perform significantly better in the game than those that watch fewer videos, as far as the number of levels they completed, the number of gold and the silver coins that they earned. And finally, and very importantly, the learning supports that were embedded in the game do not detract from the fun. Students, and this was super exciting and also surprising, because we had thought, oh, the people that get the supports it's going to take away from the fun factor. But turns out students who watch more physics videos actually reported higher levels of enjoyment than those that watch fewer. And that was significant. And finally, there's a whole range of different current and next steps. I sort of just mentioned that we've been testing student control versus computer control of the support. In the study that I just showed you, the students had control of whether they viewed supports or not. And one thing that we saw was when supports are optional, students on average are not getting enough dosage of the learning supports. There was some influence on learning. So what we're doing now is doing computer delivery of the supports. So if we're going to deliver supports to students, when do we deliver them? And we don't want to just bombard them with supports, because that would really screw things up. So we that has to do with the type of support delivery, but the timing of support is important too. Do we give the supports before a relevant level? Like this level is all about Newton's second law, and we have a physics video about that. Do we give it before as an advanced organizer, or do we give it after they completed a level so they can use it for reflection purposes? And we just recently tested 154 subjects, and there's actually not that much difference between whether it's given before or after. Just getting the supports is a good thing. There's a slight advantage for before. In terms of the type of support, we have model-based delivery versus fixed delivery. So fixed delivery is something like every 8 levels, here's a relevant support, or every 10 minutes or something like that, versus a model-based one. So we have 2 different models that are now running in the system. The first are the Bayes nets that I mentioned, and this is for delivering of the cognitive support. So if somebody falls below a threshold, say your understanding of properties of torque is really low, and so why not deliver learning support in line with that. And we also have a quick prediction model, and that was developed by Ryan Baker and his team, that can predict the likelihood of a person about to quit a level. And that's when somebody is so frustrated that they're just about out of here. And that's being used for the model-based delivery of the affective supports. And we have a lot of ongoing studies, mechanical Turk and otherwise, that are looking at affective supports. And what works and what doesn't for what kind of affective. And with that, I think my time is up. And so are my slides.